Now we come to the definition of the qubit, what we mean by a qubit itself. Here we have our classical bit, and could be in 0 or 1. So if you have a sequence of words, like for example, the word hello, you can express it in terms of the zeros and ones. It's called the machine language as a sequence. So you have a binary string of zeros and ones, like 0, 1, 0, 0, 1, 0, 0, 0, and so on. So you convert each letter using the ASCII encoding, for example, into a binary string of zeros and ones, and then this is what you see in the quantum processor, and this is what you see in the inside register of the processor. However, if we go to the quantum bit or the qubit, it can be in 0, it can be in 1, or it can be partially in 0 and partially in 1. So we call it partly in 0 and partly in 1. So you can imagine the qubit is like a racing car. So in a city with a maximum of 30 kilometer per hour. So if you have a car which has a moderate speed, both of them will go with 30 kilometer per hour. However, if you go to the autobahn, one of them will perform and will go much, much faster, maybe will exceed 400 kilometer per hour or so, because it has the ability to do so. And the quantum bit or the qubit has this ability. It has the ability to jump into the superposition and leverage the quantum properties to be partly in 0 and partly in 1. So it can exist in both situations at the same time. The superposition of the qubits allow quantum computers to perform computations in parallel, which can lead to significant speed up over classical computers. And there is huge promise of quantum computers that we can simulate much, much larger quantum systems, like very big molecular structures, the DNA, and much more. Further, it can have significant applications in stock market simulations, portfolio optimizations, and even to enhance AI models. And in this section, we are going to discuss the properties of qubits and how they are represented mathematically. So far, this table represents what I have outlined a few minutes ago, that we can express words in terms of binary, and this is how we use the zeros and ones if we want to store a word in hard disk or in the RAM or to work on it in our processor, in a classical processor. And if we have numbers, for example, in decimal format, like 0, 1, 2, 3, 4, 5, 6, and 7, this is how we can represent it in binary. So the 0 can be represented as 3 zeros, the 1 will be 001. If you have a 3-bit register, then the 1 will be 001, the 2 will be 010, the 3 will be 011, 4 100, the 5 101, 6 is 110, and the 7 is 111. And this gives you an example where we using the binary strings or the combination of zeros and ones, we can express numbers and eventually can express characters and letters and everything via different ways of encoding. And this is how classical computers and the data storage in classical computers work. We store them in bits, and each bit can carry state 0 or state 1. And based on this combination, we can express the information that we have, the numbers, and then the higher layers of letters and eventually images and so on. Now, qubits are the building blocks of quantum information. So it's a binary, or it is a 2-level quantum system, which can exist in a superposition between 0 and 1. And it has to be like this. And the 0 and 1 states have to be distinguished from one another. So they have to be completely resolved from one another without even an overlap, to be an orthogonal or completely distinguished states. So we can represent the qubit as a thing which lives in 2 states. So we have state 0 and then we have state 1. And here we can have some coefficients. What these coefficients are, those represent the overlap between the qubit and the state 0, and beta represents the overlap with the state 1. And if we square these ones, we get the probability of finding the qubit in state 0. And if we do the same with beta, then we get the probability of state 1. Of course, this is not entirely a square. So this, we call it the modulus squared of alpha, which is the complex conjugate of the number times the number itself. And this is, we express it as a modulus of alpha squared. This is a probability of finding the qubit in state 0. Similarly, beta is the probability of finding the qubit in state 1. We have to bear in mind that we are discussing a quantum particle, and it means that the total probability should equal to 1 because the particle is already there. The qubit is a quantum particle, so it has to be either in the state 0 or in state 1. It can't not be in another state because it's a 2 energy level system or partly in between. So the total probability of being in 0 or in being in 1 when we perform the measurement and the whole system collapses, this should equal to 1. So the alpha and the beta are complex numbers in general, and alpha squared plus beta squared, that should equal to 1. So as any physical system, the qubit state has to be normalized to unity, and the normalization condition is given by this formula, which both the square of alpha plus the square of beta, in the way that we have explained, should equal to 1. So now we see the qubit is a classical bit that has the ability to be in 0 and 1. However, it can jump to the quantum state and be partly in 0 and partly in 1. So that's the difference between the qubit and the classical bit. It has this ability that if you perform a certain quantum operation on it, it can be in a superposition of 0 and 1. And mathematically, we can express or represent the qubit as a vector of two-dimensional complex vector space, and the state could be represented as kit q equals alpha kit 0 plus beta kit 1. We are gonna define those now, but this is the way that we define it. Our qubit is expressed in terms of kit, and the kit which represents this particular state, we are gonna visit it shortly. And this we have alpha kit 0 plus beta kit 1. And these are the two distinguished states which a qubit can exist in. And then we have our normalization, which means that alpha squared plus beta squared, this equals to 1.